Okay, we have about 50 participants, so I think it's a good time to start. Welcome everybody for this first webinar of the Black Hole PIRE series. This is in this spring semester. We're very excited that this new series is all about advanced data analysis methods for Event Horizon Telescope observations. And as you know, this is a part of a sequence of many series that we've done in the past with both astrophysics of the Event Horizon Telescope or previous data analysis techniques. And if you're interested in looking at all the previous webinars, you can find them on the YouTube channel through the Black Hole PIRE that you can actually see right now on the chat, the link to them. We're going to have a wonderful series coming up in the next few months, and I would encourage everybody to register for all of them, look at the events and participate in all of them. And you will see right now on the chat the link for those new upcoming webinars. Today's webinar is going to last about an hour, and we're going to have time for questions both at some particular times during the webinar when the speaker asks for feedback and at the end. And I wanted to, before starting this actual webinar, I want to emphasize for everybody the importance that you feel at the end of this webinar, the feedback survey that is going to pop up on your screen. We have been making significant changes to the webinars, listening to what you have been providing, feedback that you have been providing to us, and we would love to continue doing that. But as I said, this is a link that is going to appear on your screen towards the end of this webinar. So without wasting any more time, I wanted to introduce today's speaker. We're more than happy to have Professor Mike Nowak today from the Washington University in St. Louis talk to us about time domain method analysis, both with the Event Horizon Telescope and outside of the Event Horizon Telescope. Mike is indeed one of the few people that I know that has significant expertise both in theoretical work, in time domain analysis methods, and observational work, especially with X-ray satellites like the XT, Chandra, NewStar, Swift, and many other missions. Not only has he applied those methods both to interpret and understand astrophysical phenomena, but he has also developed several of those methods himself. So we are really, really excited to have him today talking to us and giving us some introduction about time domain techniques in astrophysics and the EHD. Go ahead, Mike. Thank you very much.
All right. Thank you for the kind invitation, Dimitris, to give this talk today, and the nice words at the start here. Let me share the presentation. Okay, so I am going to talk today mostly about incoherent variability, and hopefully, as I say here, we'll do that somewhat coherently. And I'll describe to you what that means. There's a lot of shout outs to people over the years who have done work in this, mostly in the X-ray, since that's my background and expertise. I've listed a number of names here, including Dimitrios, who has something of a history in this as well. And you'll see references to all these people scattered throughout. The usual caveats being anything clever I say attributed to many of these collaborators over the years. Anything stupid I say, probably entirely my fault. So I'm going to start off with some useful references that I suggest that you can go and look at to get more information. 3 main review papers here. Simon Vaughn, who shows up a lot in the slides. He does some really great review papers on this subject. Recent one by Adam Ingram and Sarah Mata, specifically on quasi-periodic oscillations. And then there's a classic book chapter by Mikkel van der Klees from the University of Amsterdam. Dimitris has spent a fair bit of time there himself on the rapid X-ray variability. Mikkel just recently retired, but he is one of the great thinkers in this field of X-ray variability. A lot of great papers by him and a very good review chapter in the book reference there. I've also created an astrophysical database library with a lot more references than you'll find in the talk, and I put it at the URL listed there. I won't guarantee that that URL will be there 10 years from now, but it should last for quite some time. So there's a lot of references there that you can go looking through as a jump off point for digging deeper into this area, a lot more than there's going to be in the talk today. So let's talk about incoherent variability by first instead giving an example of coherent variability so we can contrast that and to talk a bit about the differences. And one of the biggest, most important recent examples is the gravitational wave signal from LIGO. And that first detection of that was from two in-spiraling black holes merging together to form one single more massive black hole, and in the process shedding the angular momentum from that process outward in the form of gravitational radiation ripples in space-time, which then propagated to the Earth and caused the two LIGO detectors in Louisiana and Washington to start oscillating back and forth, detecting the gravitational radiation. So the signal for that is shown in this figure here in the upper right corner. And this is the Washington signal, and here is the signal in Louisiana. And you can see the sort of the characteristics that one expects for the black holes, that it starts at a slow variability that gets more and more rapid as time goes on. And not only does it get more rapid, it gets stronger in signal before the two black holes merge and disappear into a single black hole, and the ringing stops. Now, this is an example of coherent variability, but what we mean by that is that we know the expected frequency, phase, and amplitude relationship of the whole process going here, that we're not just measuring the energy coming from this merger, we're actually measuring the strain as a function of time, amplitude, and phase, because we know exactly what should be happening here. Black holes, although the calculations for this waveform are extremely complex, the system itself is extremely simple. These are effectively really just 2 point sources. Black holes are described by mass and spin, and that's it. So there's really no structure there. There's no turbulence or other random variability going on in creating these waves. So we can very precisely calculate what the phase, amplitude, and frequency should be. So imagine in case of electricity and magnetism for light, rather than just measuring the energy you're absorbing from the light, you're actually measuring the displacement caused by the electric and magnetic fields as a function of time and position. That is essentially what coherent variability is. And because of that, for the case of LIGO, since you're measuring actually amplitudes and not just total power, the distance, the measurability of these signals doesn't fall off as 1 over distance squared. It falls only over as 1 over distance, because power is amplitude squared. And so if you can measure the amplitude, you're falling off as distance and not distance squared. So again, for LIGO, the case, the fact that we can have a coherent signal here is really because the system is really quite simple overall. And so what they do in this case to detect these signals is template fitting. You know the theoretical model of what the waveform should look like. So basically you do a cross correlation of that theoretical waveform with the measured noisy detector, and the peaks should line up. So when you multiply this by the signal, the negative peaks of course become positive and the positive peaks stay positive, and you get a large correlation signal. Now this is because you've got 2 black holes, and again, they're very simple as far as the waveform. The same is true for the case of neutron stars. The neutron star, for all intents and purposes, is acting as a single body. There's, in terms of the gravitational wave signal, there's nothing going on in this merger process that is contributing anything random to the signal that you're seeing. You can have deformations of the neutron star, but they're going to be somewhat global, and that does come into the calculation of the waveform for the merging neutron stars, but you don't have random turbulence contributing to the waveform throughout the merger process. So the signals are going to stay coherent. So again, you can imagine different parts of the process going on are all essentially in phase with each other. So if in this case your strain is made up of one part of the neutron star oscillating at a given frequency and another part of the neutron star merger oscillating at a different frequency, it might be phase delayed, but that phase delayed is constant relative to the other components of the system. So when I calculate the power, I'm basically taking one oscillating component and another oscillating component with a fixed known phase difference between the two and multiplying it. So the total power is going to be power squared of the two components plus a cross term with a term relative to phase that's either constructively interfering or deconstructively interfering. But there's this extra term going on there because it's a coherent oscillation. Now, imagine instead we have a system made up of various different components that are all oscillating, but they don't know about each other. That one part of the system, they might have same characteristic frequencies, but there is nothing enforcing a phase relationship between the two. In that case, we would expect the phase to be a function of time, and them not, since they don't know about each other, they're going to tend to randomly cancel out. And so the total power is just going to be the individual components squared added together. This is incoherent variability, and that's really going to be what we talk about for the rest of this talk. So because in the case of LIGO, there are these coherent relationships, one can use templates to match frequency and phase. With incoherent variability, there really is not this concept of templates to match phase and frequency. And therefore, the individual components of the system are really going to be this incoherent sum. Now, I'm going to start off by apologizing by talking about noise. In a sense, I'm going to use the term noise a number of different times. Noise can be either referring to the signal from the source or the measurement process. But in either case, when we talk about noise throughout this talk, realize that all of this is going to be incoherent processes adding together. Different components will have random phases that don't know about each other. So noise in terms of the signal from the source or noise in terms of the measurement processes could have well-determined amplitudes, but undetermined phases. And so when we add these processes together, we're going to be doing this incoherent sum where basically we're summing amplitudes squared without any reference to phase. So as I just said there, I'm going to use the term noise and also, unfortunately, later the term coherence in several different ways. Noise can refer to measurement uncertainties of variable processes. Now, from my perspective as an X-ray astrophysicist, most of the detectors I work with are counting photons. X-rays come in as discrete events. There's not an awful lot of them, and we're counting individual photons. And when we're doing that, we are subjecting the measurement process to Poisson counting noise. So if I have n events that I expect to occur in a certain time, what I'm really going to measure is n plus or minus the square root of n. So that is essentially Poisson statistics. Our life in X-ray astrophysics is ruled by Poisson statistics. Poisson becomes Gaussian in the limit as we go to very large number of events. But in many cases that we're going to see here, X-ray astrophysics, we can be fairly small, and we have to actually worry about the number of events that we're actually measuring. So that will be one term of noise. It's just the measurement noise in the system. But for incoherent variability, we often talk about the variable processes themselves and refer to those as noise. And I'll give you some examples and some definitions here. You'll often see in the papers that are referenced in the library and in this talk things would be referred to as white noise or red noise or band limited noise. And I'll show you examples of all three of those. And those are ways of characterizing incoherent variability processes. But before we get to that, we're going to take a step backwards and start with kind of one of the most basic questions we often ask in X-ray astrophysics. Is my source variable at all? And what are the tests, some of the tests for variability? And there's many ways of answering this particular question. And usually what we do is base these tests on the Poisson noise properties of the measurement itself. That is specifically for a constant rate source, we expect the rate, the time between events coming into our detector to be Poisson distributed, that one time to the next time event, those times are completely uncorrelated with one another. And there's a characteristic waiting time labeled here tau, and there's a probability for what time I'm going to measure that goes exponentially. And the average of this is you have an average of the waiting time of tau, but you can have events that occur more close to each other than that, or several times longer than that. And I'm going to give you an example relevant to the Event Horizon Telescope, the example of Xray star, the supermassive black hole at the center of our galaxy. So you probably heard a lot about Xray star recently, especially with the recent Nobel Prize awarded to Andrea Getz and Reinhard Genzel for measurements of the mass and effectively some constraints on the size of Sagittarius A star in the center of our galaxy. It's about 4 million times the sun in a very compact region at the center of our galaxy, based upon measuring orbits of infrared emitting stars going around the center of the black holes for roughly the past 25 years. They've been doing this to the point that some of these objects that they've seen complete orbits around the black hole. So that's shown here on the left. On the right is an observation that I did with some collaborators using the Chandra X-ray telescope. This is an X-ray observation of the center of the galaxy. Here is Sagittarius A star in the center of the galaxy. And it took the Chandra X-ray telescope to actually make these measurements because Sagittarius A star is very faint in the X-rays. And you can see it blinking there. And this is a little loop of a movie that we did. And we're going to talk about that in a second. Roughly once a day or so, the brightness of Sagittarius A star increases from a fairly faint level to roughly a factor of 10 to 100 or so times brighter, with typical time scales of these flaring events to be on the order of 6.
1 second. Can you guys still hear me?
We can hear you, Mike.
Dimitrios?
Yes. Can you hear me?
I am.
Apologies for the technical problem.
My microphone, my headphone just went out. So Dimitrios, could you wave or something if you can still hear me?
We can hear you.
Okay, good. I'll keep going then.
Thank you.
Very good. Okay, so I was showing here that this is the X-ray observations of Sagittarius A star. We can see it blinking on and off. And the time scale of this blinking is giving an idea of the size of the system. It's consistent with being a very compact region, only a few times larger than the event horizon of the black hole. So here are light curves of Sagittarius A star in the X-rays. And you can see on the left is a typical observation. And what I've plotted there is the number of counts per 200-second time bins. over a course of roughly 30,000 seconds. This is typically what...
Mike, we see the
I cannot hear you, Demetrios.
We
we
still see the last slide.
Oh, okay. You still see the last slide.
Yes. Perhaps you might want to restart your...
I will stop the share. Okay. Okay. And how's that?
Next slide.
Slides changing? Excellent. Okay, sorry about that. Of course, technical difficulties. My headphones just died in the middle of this. So I had to switch over to manual. So anyhow, we see here the light curve on the left, and this is a typical Sagittarius A-star light curve in the Xray. And we're seeing counts per several 200-second bins. And you can see here the typical bin, it's coming in very slowly, 0, 1, 2, or 3 counts. That is completely consistent with no variability, constant rate. That's just the expectations that you expect from counting statistics, Poisson counting statistics. However, on the right, we show a light curve where we see some of these flares. And we've searched for these flares by looking for changes in the Poisson counting statistics. And you can see in this particular observation on the right, there are 3 flares. And this is a method developed by Jeff Scargill from Ames Research Center in California. And he's come up with a clever algorithm. You can imagine if I have n events in this light curve, that I can, between any 2 events, put a partition and answer a yes/no question. Does my rate change across this partition? And if there are n events, there are n partitions possible. So there are 2 to the n possible different light curves. And he's basically come up with a method of searching all of those 2 to the n possibilities and saying, is the probability of 1 block more significant than the probability of 2 blocks? And doing that comparison and then optimally putting in the partitions of the light curve. So that's essentially what this variability search does in the X-rays for Sagittarius A-star, is solve that 2 to the n problem. And you can see here that it's gone and found several different points where the light curve has changed and significantly become brighter. In this case, there are 3 flares going on, based again upon the fact that it's Poisson statistics. And here's another example of one of the 4 or 5 brightest flares we've ever seen from Sagittarius A-star. This one was a bit more obvious to see with this method. Now, we see roughly 1 flare per day. We believe that the fainter ones are more common. We see more of the fainter ones. We can show that statistically. But what we really can't do are the flares correlated. You can see here 2. Is that just a random occurrence that 2 have happened at the same time? Or are these 2 small flare and large flare related to each other? Do the amplitudes and rates change with time? For example, if one of these other stars comes very close to Sagittarius A-star, does the rate of these flares increase? These things are still under debate. There's a paper I point to there in the ADS library. We don't really know yet. There's not a lot of strong evidence, mostly to the fact that we've got very limited observations. We have roughly only 40 flares that we've seen over roughly 40 days of observations over these past 20 years. And so we don't really have the statistics. So the next part of the talk, I'm going to start talking about examples where we can characterize the statistical properties of variability. So I'll pause briefly here and ask if there are any questions at this first third of the talk.
Thank you, Mike. And for everybody, please write your questions in the Q&A or in the chat if you have any. And to get things going, I have a quick question for you, Mike. You talked about the Scargill approach to identifying whether a process is Poissonian or not. Is that trivially generalizable to non-Poissonian processes? If I have the distribution of a noise, like, in VLBI, there's a completely different noise structure, would it be trivial to generalize and ask myself whether there is evidence for variability outside the noise?
Yeah, actually it can be generated. You just really, the cleverness of the algorithm is in the way it optimally searches through the number of the 2 to n possibilities. The actual calculations it's doing is really just based upon whatever properties of the statistics. You can choose Poisson, you can choose Gaussian, you can choose other things. So as I said, the cleverness is in the way you do the division, but everything else is just swapping out the probability distribution one for other. And in fact, you can also further generalize this. Instead of being a time series, it could be a spectrum, and you could be looking for emission lines or absorption lines, and formally it's the same thing in that particular case. So it's actually quite a clever algorithm. It's a little slow. It's n squared is how fast it runs, but since it's solving a 2 to the n problem, n squared is pretty good.
I agree. We don't have any more questions right now, so go ahead and please, everybody, you can feel free to write questions during the presentation. We'll bring them up at the breaks.
So we're now going to switch to talking about variability as an example of Xray binaries. And an example of that, I'm going to present Cygnus X1, which is a black hole Xray binary in our galaxy. It's about 2 kiloparsecs away. The black hole is roughly 10 times the mass of the sun. And there is a roughly 20 solar mass star orbiting around Cygnus X1 every 6 days. And material is being pulled off the atmosphere of this companion star, falling on to the black hole because it has angular momentum. It has to form an accretion disk. As that material falls in the gravitational potential well of the black hole, it releases gravitational potential energy, which is turned into light and heat. And because this object is very compact and dense, typically most of the energy is going to be coming out in the X-rays, very powerful X-rays at that. And so here is an observation of roughly 5,000 seconds of observations of Cygnus X1 taken with an X-ray observatory, NICER, which is flying on the space station right now. It measures X-rays at energies between 300 electron volts and roughly 10 kilo electron volts. That's equivalent to temperatures of roughly 1 million degrees to 100 million degrees. And what we can see here is very large amplitude variability. This is a light curve on 10-second timescales. The blue is the light curve, and if you can see the orange there, the orange bars are the amplitude of the expected statistical noise just from the counting statistics. And you can see that the variation due to the counting statistics is essentially negligible in this case. All the variation that you see there is due to the light curve itself. Now, there's nothing obvious in this. There's no obvious periodic patterns. It looks what we call noisy, but it's going to turn out that this noise is very structured. So how do we go about characterizing this noise? Now, before we do that, I'm going to show you this variability on different time scales. Here we have a 10-second light curve. If I take the same segment and go to 1 second, you can still see that the Poisson noise is essentially negligible, and the variations are slightly larger amplitude. You can see now we have 7,000 up to 7,000 counts per second. And there is variations even on this 1 second time scales. What if we go to 1/10 of a second? We have even larger variability still. We have up to on the order of 20,000 counts per second, which is still beyond the counting noise that we see in the system. And we have variability even down to this 0.1 second time scales. So how do we go about characterizing this? And the most common methods that you'll find in astrophysics, especially X-ray astrophysics, is to start talking about Fourier methods, breaking down this variability into its component timescales on different characteristic timescales via the use of Fourier transforms. So for a continuous infinite light curve, a Fourier transform is just a transform from the time domain to a frequency domain. So we could write any time series as an integral of a function, the Fourier transform, that's a function of frequency multiplied by an exponential at a given frequency integrated over all frequencies. And we can invert that function by doing the opposite integral over a function of time. And this is called the Fourier transform pair. So we can write any light curve in terms of its constituent time components or constituent frequency components. Now, of course, in X-ray astrophysics, we don't have continuous light curves and we don't have infinite light curves. So what we do instead is look at these discrete light curves and these finite times, and we divide these finite times into segments. And we're going to presume that each of these segments are statistically identical to each other. And typically, we divide the light curves into segments on the order of 100 to 1,000 seconds. Now, there are two reasons we typically choose timescales on the order of 100 to 1,000 seconds. I'm going to show you a little bit later in talk that covers a wide range of characteristic timescales in the light curve itself, but more importantly, just the practicalities of observations. Most of the satellites looking at these objects are orbiting the Earth. They go around the Earth roughly once every 5,000 seconds if they're in near Earth orbits. And very typically, they do not have the ability to look at a single object for much longer than about 2,000 seconds or so. So for many of these spacecraft, you rarely get a continuous unbroken light curve that's longer than on the order of 2,000 seconds. So that's typically what the longest timescale segments tend to be, on the order of 1,000 seconds. Now, the assumption that we're going to make for these light curves is that each of these segments is statistically identical from one segment to another. And this is a concept of statistically stationary. It's an actual mathematical concept. There is a book on noise analysis I put in the library, Davenport and Root, which gives a much more rigorous mathematical definition by what we mean statistically stationary. But for purposes of this talk, what we really mean is that each of these individual segments is a fair statistical sample of the overall light curve. And rather than doing a continuous Fourier transform, we're going to do a discrete Fourier transform that we're going to apply this transform to counts per individual time bins rather than a continuous function. And rather than it be an integral, we're going to do a sum. And so here's the Fourier transform written as a sum. And all we can do is a sum from the shortest time bin to the longest time bin. And so if we have n events, we turn that into a Fourier transform that goes from a frequency, a negative frequency, to a positive frequency, where the frequency binning is 1 over the time. The smallest frequency bin is 1 over the total time scale of the observation. And from that, we can create what's called the power spectrum, which is just the squared amplitude of the Fourier transform. It's giving you an idea of how much variability at a given frequency is there. The larger the power, the more the variability is characterized by that individual frequency. Now, what we do in doing this process is that we do two averages. We average over the number of segments that we have for the light curve, and also we typically average over adjacent frequency bins. And we usually do a logarithmic averaging where the number of frequency bins is increasing that we average over as we go to higher and higher frequencies. So delta F over F, typically on the order of ranges of 5% to 20%. And you're going to see this coming up in the talk. So for real valued light curves, which of course all our light curves in astrophysics are, the negative frequencies and the positive frequencies are actually symmetric with each other. The power is the same. So we usually only show positive frequencies when doing our plots of Fourier transform power. And so that's called a one-sided normalization. And furthermore, we usually choose a normalization of this where we multiply by that factor of 2 from positive and negative frequencies and divide by the total time of our observation and divide it by the mean rate squared of our observation. When we do that, if we integrate the power spectrum over frequencies, what we get is the fractional root mean squared variability, the percentage of variability relative to the mean in a given frequency range, or we get the square of that, and then we take the square root to get the fractional variability. So usually what you're going to see in the rest of the slides here, my y-axis for the power spectrum is going to be labeled as root mean squared per unit hertz. So taking the integral over a range of frequencies, and then taking the square root is giving me the fractional variability over that frequency range. So in this formulation, Poisson noise is going to come into this with a power spectrum level that goes as 2 over the rate. The power spectrum will not, for the source, the variability property of the source itself is not going to change as a function of the rate, but the level of the noise is going to change with the function of rate. Very low rates, the noise level is going to be high. Very high rates, the noise level is going to be low. So here is that same Cygnus X1 light curve from the NICER spacecraft. Now I've taken the power spectrum in these 1,000 second, roughly 200 second segments up to a frequency of 1,000 cycles per second. And you can see here that we have flat parts at low frequency and high frequency. The flat part at low frequency is part of the noise, the variability process of Cygnus X1 itself. The flat part at high frequency is the Poisson noise of our measurement errors coming in. In the middle, we've got a part that's roughly going as 1 over frequency. And towards the end, we've got a part that's going as 1 over frequency squared. Now, these get different labels. Anything that has this characteristic flat 1 over f squared shape to it is called band limited noise. Anything that has a 1 over f shape is called red noise. Anything that has a flat shape is called white noise. And you can see all 3 of those structures there in Cygnus X1. So the properties of incoherent power spectra is that for any given signal segment we do, at a given frequency for that power spectrum, this is a complex quantity. It has an amplitude and a complex phase. The phase is completely random for each individual frequency bin and each individual segment, but the amplitude has a very well-defined mean at a given frequency. However, for one segment and one frequency bin, that mean essentially has 100% error to it. There is some, for the infinite light curve, there's some well-defined average, but for that one individual segment, the power spectrum for that one segment is not a good representation of that mean. You have to average very many of these together to get a good measurement of that mean. On top of that, we have the measurement counting noise, which is completely independent of the variability processes themselves. So the amplitude of the variations to the counting noise can be estimated and subtracted. This counting noise is going to be distributed evenly across all frequencies. Counting noise is essentially white noise. Again, it has a very well-defined amplitude independent of frequency and completely random phases. There are some detector effects that can put some structure into the Poisson counting noise. And I've got some references there in the library, especially this very good reference by Will Zhang from 1995, but that can be modeled and taken out. Also, sometimes in the literature, you'll see these alternative power spectrum normalizations where the Poisson noise, instead of being normalized to 2 over the rate, will be normalized to the 2. Those are the two things that you'll see very often in the literature. So here is that same Cygnus X1 power spectrum with the Poisson noise subtracted out of it. So that flat part at high frequency has gone away, and you can see a little bit better the f to the 0, 1 over f, and 1 over the f minus 2, 1 over f squared structure of that power spectrum. And in fact, we can highlight that a little bit more by multiplying by frequency to show that structure. Multiplying by frequency really is giving you an idea of what the integral is like. So looking at the power spectrum, multiplying by frequency, we see where the largest contributions to the integration of the power spectrum is, which is really saying in the case of Cygnus X1, most of your variability is lying between 1/10 of a second to 10 seconds. This helps justify a little bit of only going out to segments of roughly 200 seconds, is that there's not a lot of variability power there going on, that we're capturing most of the structure of the variability by looking at these 200-second segments and going out to 1/1000th of a second to get frequencies on the order of 1,000 hertz in this particular case. Now you'll see that when we multiply by frequency in this case, the structure really isn't quite such like a broken power law. There's a little bit more structure to it than that, and we're going to talk about that in a second, is that the structure is more complex than just simple power laws going on here. But we're going to take a step back. Sometimes for other sources, that structure becomes a little bit more obvious. You get things called quasi-periodic oscillations. If this were a periodic oscillation, that peak you see there roughly at 6 cycles per second would be narrow and very strong. Pulsars basically show up in power spectrum as large peaks in almost one single frequency bin of the power spectrum. Quasi-periodic oscillations, you can see here, exist over a range of frequency bins and at lower amplitude. It still kind of looks almost like a periodic signal, but not quite. We define what's called, and apologies here, coherence, the Q factor. Again, we're going to use coherence in like 3 different ways in this talk. The Q factor is the frequency of the feature you see divided by its full width half maximum. And for quasi-periodic oscillations, if that width is on the order of 1 to 10% of the frequency, we call that quasi-periodic. Now, quasi-periodic oscillations is actually what you'd expect if you had, say, an oscillator system, a driven oscillator with, say, a spring constant gives you a characteristic frequency for that, that resonance system, but you put damping in the system at the same time. So the damping factor gives a width. And so if you randomly, stochastically put a turbulent driving on a damp-driven oscillator, a response like this where you see a characteristic frequency but with a broad width is exactly what you expect for a driven oscillator. The Q factor, this quality factor of coherence, that can come about from a lot of different means. For one, for a damp-driven oscillation, the phase does not stay coherent for very many cycles of the response in that particular case. So the Q is roughly the number of periods for which the oscillation phase maintains a well-defined relationship from one cycle to another. So for Q of 10, it lasts roughly on the order of 10 cycles. Also, a random walk in frequency can give you something that looks like a QPO, or a random walk in amplitude of an oscillation can also give you something that looks like a quasi-periodic oscillation. This is described a little bit more clearly in the review paper by Ingram and Mata. So whether it's a random walk in frequency, or whether it's a random walk in amplitude, or whether it's a random walk in oscillation phase, the Q is roughly the number of cycles for which you maintain a coherent relationship for this random walk. Now, there's a few other things that you have to worry about when doing Fourier transforms. You have discrete Fourier transforms. You have to worry about aliasing and windowing. The power spectrum from a discrete Fourier transform is only an estimate of the true power spectrum of the intrinsic process. We have to worry about the fact that we're sampling at discrete times, not continuous times, and that leads to this concept of aliasing. We have to worry about the finite length, and that leads to the concept of windowing. Now, the maximum frequency we can go to in a discrete Fourier transform is called the Nyquist frequency. It's equal to 2 divided by the shortest time bin that we have. But there can be power at higher frequencies that you're not measuring beyond this Nyquist frequency. If I'm doing discrete samplings of a continuous light curve, that higher frequency power gets folded back into the power spectrum. I measure it at lower frequencies. And that's called aliasing. For X-ray astrophysics, that tends to be mitigated somewhat by the fact that those individual times, we're not taking a discrete measurement of an amplitude at that time. We're actually integrating over the bin, the number of counts that comes into that full time bin. So we're averaging over that, and that tends to drop down that aliasing. So for X-ray astrophysics, it tends not to be a concern. Now, so going back to Cygnus X1, you can also see that the power is dropping off so rapidly at high frequency that there's also not really much anything to be aliased back into our lower frequency variability. For windowing, this comes to the convolution correlation theorems, that a convolution is basically taking an external function and smearing my light curve over this function. It could be a Gaussian smearing of our signal, and that's convolving a Gaussian with my light curve. And it turns out that for the Fourier transform of a convolution is equal to the Fourier transform of your input signal times the Fourier transform of the convolution itself for the window function. And the inverse of that is true. And a convolution is also more or less the same as a correlation, except for a change in the sign of that you put into the interval. Instead of a minus x, you have a plus t plus ta, and you're relating two signals, and you're kind of sliding them back and forth to each other and saying, when did they line up with each other? There is a peak there, and the correlation is going to be high. So my discrete segment sample is essentially doing a convolution of my continuous light curve with a step function here, that it's 0 on either side of my segment, it's 1 in the middle of the segment. This is multiplying to a continuous light curve and a step function together. And that, when I take the Fourier transform, is equivalent of convolving the Fourier transform of the step function with the Fourier transform of my light curve. The Fourier transform of a step function is this kind of Gaussian function with little tails going off. So I'm convolving my Fourier transform of my intrinsic process with the Fourier transform of the step function. And so I can be taking high frequency, I could be taking power from low frequencies, and with the convolution, putting that power to high frequencies. And so that can confuse a little bit my estimates of the power spectrum in this particular case. So it tends not to be a huge issue for us if the power rises slowly to low frequency. The fact that in Cygnus X1, we've got the power cutting off as a flat f to the 0 at low frequency means that it's not going to be a huge issue. But if there were significant power at that low frequencies, then we might really have to worry about it. We can mitigate it also by going to longer observations, but that's not necessarily always a possibility. Now, let's go back to Cygnus X1. I showed you that when you multiplied by frequency in the case of nicer observations, you saw more structure there. NICER is a relatively new spacecraft. We have fewer observations with it compared to some historical spacecraft. This is an set of observations from the Rossi X-ray timing explorer, similar properties as to NICER. This flew from 1995 to 2015, if my memory serves, and there were a lot more observations, deeper observations to go into. So this is, again, Cygnus X1, looked at in the X-rays, similar bandpass to what we saw with NICER, but longer and less interrupted observations. So we have better statistics for this case. I've done the same thing. I've taken a Fourier transform and I've multiplied by the frequency to show you where the power is coming from. And you can see what looked like kind of a broken power law really has a lot more structure to it, that we have what looks like these individual broad, almost quasi-periodic components. These will be kind of almost QPOs with a quality factor of order 1. The question is, are these processes, do these individual components really represent individual processes? And I think the answer in this particular case is yes, because we can actually do correlations of these individual processes with other properties of the system. So I can measure, you can see in this case, there's four characteristic frequencies going, and I can relate those to the spectral properties of Cygnus X1. The spectrum of Cygnus X1 is usually described as a power law. On the left index is the slope of this power law. At the bottom really basically means more of my energy from Cygnus X1 is coming out at higher X-ray energies. The top of the y-axis is more of my energy from Cygnus X1 come from lower energies. And we can see as the characteristic energies of the spectrum from Cygnus X1 goes from low energy to high energy, the frequency of these oscillations very smoothly along with that the frequencies tend to become higher. And the frequencies are characteristic of very much the inner region of the black hole. The top there labels the distance from the black hole for orbits going around the black hole in units of essentially the Schwarzschild radius, or half the Schwarzschild radius. So these are timescales consistent with being from 20 to 70 times the Schwarzschild radius of Cygnus X1 in this particular case. And you can see that this is kind of indicating something is structured going on. Likewise, the amplitude of these variations tends to vary with both frequency and spectrum in the system. And a possible way of interpreting this is to consider that we have maybe a disk on the outside of the system that's transiting to a combination of a corona and or a jet in the inner system. And the disk is a source of turbulent noise that's being filtered through a transition region. And then we're seeing that response in the corona and or a jet. So we can maybe view the disk on the outside as a noise source and the jet on the inside as the response of that noise source. And so this might be our damped driven oscillator in the particular source. And this actually, there's a great paper by Dimitrios on this, Saltis and Norman, 1999. The best unpublished, most highly cited unpublished paper I know of that never got published. Dimitrios can tell you that story, but it's a great paper and it's had a lot of influence about the way people think about this. And so you might imagine that this is our driving and response system. And as this region, this transition between disk and jet moves in and out, the spectrum changes as well at the same time as the frequency and amplitude of these response components change. So that's one of the nice reasons for looking at things in Fourier space. All right.
Mike, I will interrupt you for a second, just because we're at the 57-minute mark,
yeah.
And just to give you an idea where we are with time.
So I'll stop here and take questions because I've got a few more pages on other stuff. We can go onward, but let's give people a chance to ask questions about this first part, the second part here, and we can decide how much more to go onward.
We can, do you want to, I mean, if it's only a couple of slides in a couple of minutes, you can do it, because we had some technical problems that we can filter out.
I apologize. You know, I thought I had the headphones charged.
It's totally fine. Why don't you spend a couple more minutes to finish what you have, and then we can move on from there.
So the next piece, now what I've been showing you is doing the power spectrum in one energy band at a time. And those four components there don't necessarily know about each other. They can be incoherent with one another. However, we can do this in multiple energy bands. I can look at, say, 1 keV and look at the variability and compare that to the variability in 10 keV. And I can do a cross correlation between those two energy bands. And so rather than looking at the amplitude of the power spectrum, I can look at the amplitude and phase of the cross power spectrum. Again, I'm basically just doing a correlation between the two energy bands. And then if I do that in Fourier space, I'm taking one Fourier transform, taking its complex conjugate, multiplying by the other Fourier transform. I have an average amplitude, and I also have a phase between the two. So the question is this phase between these two incoherent light curves, does that have a characteristic relationship that's well measurable? And the answer is yes. So I can take that complex phase in Fourier space, divide by the frequency, and that we call a time lag. It might not be strictly a propagation time lag, but it is a time lag nevertheless that might give us some physical information. So here I'm doing that for Cygnus X1. The lower light curve is low energy. The upper light curve is high energy. I've divided that into segments. And each segment, I show you the phase of the Fourier transform, the average phase of the Fourier transform at a given frequency. And I think in this case, I'm doing 10 Hertz. And you can see that from segment to segment, that the phase is kind of randomly walking. That's because it's an incoherent process. But when I do the cross correlation between the two light curves, and I'm showing that in the middle, the average of the cross correlation between the two light curves is very well defined, which basically means that there is a phase relationship between low energy variability and high energy variability, which can be a function of frequency and which can be a function of spectral properties. So in terms of this cross correlation, I can also do a normalization of this to determine an average normalization to determine how well is that phase defined. If that phase is very well defined from segment to segment, the normalization, which I've got here, which is called the coherence function, is going to be 1, which basically means all the segments are nicely lined up in relationship between these two energy bands. If there's a lot of scatter with that the processes really don't really correlate perfectly, it's going to go to 0, and of course could be anywhere in between. Turns out for most black hole binaries, when we do this, the correlation is extremely good, and this correlation is essentially 1, which basically means that there is some sort of transfer function from variability at low energies to variability at high energies. That transfer function is linear and very well defined in a statistical sense. However, it doesn't necessarily mean that the time delay that you're measuring is strictly a propagation time delay. Things can get complex just from the way the properties of Fourier transforms. For example, if I have a wave going out in 3 dimensions, I can look at the response of that wave via Green's functions. For 3 dimensions, that response is a delta function. And a delta function has a Fourier transform, which is a constant, which basically means that the phase I'm going to measure really is just a single time delay. However, if I got 2-dimensional propagation, the Green's function is not a delta function anymore. Instead, it's a step function with a tail behind it. And just the fact that it's a step function with a tail introduces structure into the Fourier transform. And my time delay, even though it's related to a simple propagation, as a function of frequency is going to look more complex than a simple time delay. So just the geometry alone might introduce structure into these time delays, which makes it a little bit difficult to characterize in terms of maybe simple intuitive understanding. So these time delays can be measured, and again, they're going to have relationships between hard and soft, and we do see those going on in the system, that a characteristic time delay, like the characteristic frequencies, varies with the properties of the system, and we can measure that. So it's really telling us that there is something interesting going on that might be related to the physical processes and give us clues about what's going on. So I think I will end with this last picture here, that this is showing all 3 properties for Cygnus X1. On the left is the power spectrum. On the right lower part is this phase delay or time delay. And on the top of that is this coherence, or 1 minus the coherence, showing it how well that phase delay is defined for each of these frequencies. As I said, for Cygnus X1, that phase delay, that amplitude is nearly 1, but it's not exactly 1. So that's why I applied as 1 minus the coherence. And you can see that we have these 1, 2, 3, 4 processes. Each one of these processes might have its own intrinsic time delay that adds up to the net time delay that you see in the middle there. And where the power of the components overlap, you'll get little drops in the coherence, which basically saying is that rather than having 1 driver and 1 response in Cygnus X1, we might have 4 individual incoherent processes happening independently in the system, and where the frequencies and the powers are comparable, they incoherently add, and we see a net time delay that's a little bit different than the time delay that one would associate with either one individually. And we see a net drop in the coherence, indicating that these really are 2 independent processes crossing over. So rather than having 1 process to describe in Cygnus X1 with a model like I showed you earlier, we probably have something more like 4 independent processes. All right, so I probably think I will end it at here. That the use of Fourier methods are very common because we can think of them in terms of these linear responses and linear inputs and responses to the system. And it gives us an idea of where the variability power is happening. However, I'm going to say that there are other processes, and I'm going to leave them in the slides. You can take a look at these other ways of looking at this in other domains that give us other information. Fourier transform methods are just one way of doing this. So I will stop here and start taking questions.
Thank you very much, Mike, for the really nice and extensive summary of all these methods with wonderful applications and examples. We have a couple of questions, but before we go through that, since we're past the hour mark, if anybody would like to leave and follow the rest on YouTube, please don't forget to fill the feedback form that is on the chat link. please, it's very important for us in order to improve the quality and the way that we handle these webinars. So a couple of questions for you. One was a little earlier by Samir when you were discussing the nicer observations and the noise. The question is the noise in the nicer observations chaotic?
I'm not sure exactly what you mean by chaotic. Again, the fact that it's structured shows you that there's something physically going on there. That the fact that in the nicer observations, just like I showed for the Cygnus X1 observations, you can fit 3 or 4 well-defined components to that overall noise that have well-defined frequencies and widths. I have not gone through the nicer observations to enough yet to say whether the same relationships between spectra and variability processes exist, but I would be very surprised if they didn't in nicer. It's just a matter of nicer observations tend to be a little shorter than the old XTE observations, and there's fewer of them at this point. We had 20 years with XTE to do it. So from that point of view, they look as structured as they did in the past. The one advantage with nicer is that XTE stopped at 3 kiloelectron volts, whereas nicer goes all the way down to 200 electron volts. So another factor of 10 gets us further away from corona and closer to the disk in the system. So there's interesting information to explore there with this variability.
That is actually a good segue to the next question by Gabriella, who is asking, in your F frequency times power graph for SIGX1, how does one reach the conclusion that the variability is driven by the disk? If there are other interpretations, how can one disregard them, like the source of the driver?
There's definitely is other interpretations, and the answer is that's your job as a graduate student or a postdoc. There is still work to be done there, very much so. I think the key is to use the fact that the system changes, and we have multiple observations. So the goal would be to try to come up with a model that correlates the spectra and the variability. The answer is we don't know that it's necessarily being driven by the disk, but it's a good starting hypothesis because we know the disk starts far out from the system. It starts in the optical and the infrared, and then that material moves inward. And as it moves inward, it starts radiating at the higher energy. So you can imagine as the material moves inward, it is moving inward with turbulence and noise. So at least from that point of view, I think is why people think about disk to corona a jet, because we know the jet originates towards the center, and we know the accretion disk originates towards the edge. And so that's one way that we tend to think about what's going on. But that way might be completely wrong. Mm-hmm. And so it's very definitely worthwhile thinking of alternatives and how those alternatives interplay between spectra and variability.
Thank you. We have a question from Maciek. How do we practically diagnose if statistical stationarity is a good assumption to a particular problem? I think practically is the key word here.
So I think to some extent practically is to verify that the statistics of averaging these segments together is comparable to the statistics that you expect from a statistically stationary process. For example, if the variance turns out to be larger than you would expect from a statistically stationary process, that would be one indication. You could also go to shorter and shorter subsegments, or you can take subsegments of your subsegments. If your low frequency power for your first 10 segments is different from your low frequency power for your next 10 segments, you can start comparing those. That would be a very good indication. In fact, there are definitely cases where on some level, we know that Cygnus X1 is changing its light curve from hard to soft. So if I go to weeks, obviously it's no longer statistically stationary. So for the most part, it's the timescales that we're looking at. If the spectral properties are really changing between your segments, it's probably not statistically stationary. And likewise, I said you can start looking at the statistics of your variance and see if that's consistent with statistically stationary. That's unfortunate. I wrote too much talk. I apologize for that. I skipped a bit at the end, and please look at those slides that there are cases where you can clearly see the characteristic frequencies changing over the time scales that you're looking at. And this is certainly the case here with a binary SMCX1. This is essentially a rolling power spectrum on long timescales. There is a peak in that power spectrum. The y-axis is frequency, but you can see that that is very strongly changing as a function of time, and that's not statistically stationary. So in this case, Fourier transform methods are not your best method going forward. You want to either go to the time domain or a hybrid of the time and frequency domain to account for the fact that your properties are strongly changing with time. And this is a very good example where you can clearly see that the characteristic power spectrum is changing with time. And this particular case, what looks like a continuous change in time with power spectrum methods, when you do hybrid time power spectrum methods, which is what the Hilbert-Wang transform there is referenced, you see that the changes really are discrete, that from one individual period to the next individual period, there are these stochastic jumps in characteristic time scales rather than a continuous smooth transition. And that's clearly a case where statistical stationarity is a bad assumption, and you'd want to use a different set of methods.
I guess you hope that there is some scale separation between the long-term variations and then the short-term variations so that you can chop it somewhere in between and hope
we
for
clearly have that
stationarity.
a case with Cygnus X1, because you can see, I said when you do F times the power, you can see that one end it's low, the other end it's low. So everything is in that middle of the segment. And so that's a good case of using it. For in terms of event horizon telescope, one of the tricky bits that we have is that the observation lengths are on the order of the expected observation timescales. Those flares I showed you in Cygnus X1, they're 2 hours long, and the EHT observations for a night are maybe 10 hours long at best. So we're kind of getting to the observation length is on the characteristic time length. So in that case, the Fourier transform methods might be not the best approach for that particular case.
Yeah, and also the windowing of the observations is not equidistant, the individual segments. So taking Fourier transforms is highly biased by that. We have one last question that I would like to go to before we finish by Federico. He says, regarding the 3D and 2D Green's functions, could you explain how this translates to power density spectrum frequencies?
Again, I apologize. I went over that pretty quickly. It's just that as I said, if there is a very simple input response with a single propagation time delay in 3D at all Fourier frequencies, you're going to see that same time delay, just because the Green's function is a delta function in 3 dimensions. And so point A at some time t later translates to point B. And so when you do the Fourier transform of a delta function, it's just a constant. It's that same time delay everywhere. It's essentially because in 2D, you're dealing with things like Bessel functions instead of a delta function. So it's a step function with a tail. That mere presence of the tail, and it really is just a mathematical artifact in some sense, there's Fourier structure in that tail. So yes, you'll have a time delay associated with the step, but then you have all the frequency structure associated with that tail behind it. And in some ways, it almost looks instead in 2 dimensions that rather than having a constant time delay, you get this constant phase delay. It's not quite a constant phase delay, but it's close. So it's this kind of just an artifact of the mathematics that odd number dimensions, it's a delta function. Even number dimensions, it's a step function with a tail. And so that just is kind of like a warning that the time delay is not always simply interpretable as strictly a propagation time delay. That there's not that the physical intuition of this one-to-one correspondence between a propagation delay and the measured Fourier time delay doesn't necessarily hold. It can be more complex than that. So that's just more of a bit of a warning, because a lot in the literature these days, you'll see these references to reverberation mapping. And I think that's a little too simplistic in a lot of cases, that you're looking at input and response, which are almost on top of each other, undoubtedly have these effects in them, like these 2D wave propagation. So trying to say, aha, this is the source oscillating at the jet, which is then reverberating from reflection from the disk. And I measure this time delay and say that's exactly a propagation time delay. I think the answer can be much more complex than that. So really, that's just a warning not to take such a simple interpretation, but to develop a model that does it a bit more carefully. And I think the other warning in this is that, you know, a lot of these recent models I've seen for black hole binaries is presuming one process, that this whole power spectrum is really describable by one thing. And I think when you look at it more carefully, it's always 2, 3, or 4 things going on simultaneously that you have to pull apart. And that's the other bit of, I think, that needs to be considered in these, and that you have to, what the time delay that you're actually measuring in Fourier space really might be a incoherent sum of 2 or more time delays that you have to independently model.
Thank you very much, Mike, for your presentation and for answering those questions. Thanks to everybody for joining today's webinar. And please, before